You paste a policy PDF into a chat assistant and ask, "Does this mention AES 256 anywhere?" It replies confidently, "Yes, see section 4.3, and even writes a polished sentence that sounds exactly like your document's tone. You scroll to 4.3. Nothing. The paragraph doesn't exist. Here's the strange part. The AI isn't glitching. It's doing its job. It's producing the words that, given everything it has seen, are the most likely to come next. Think of it like a supercharged autocomplete. Not a truth engine, but a probability engine that's been trained on mountains of text to be very good at sounding right. I'll be honest. This took me a while to really get. We expect an answer machine, but we're using a pattern machine. Once that distinction lands, a lot of hallucinations suddenly make sense. To put it simply, when models generate, they chase likelihood, not reality. Here's how that plays out inside the model. It starts with training on truly vast text, books, websites, documentation, billions of words. The model sees a sequence of tokens, small chunks of text, and tries to guess the next one, again and again. That guessing game is the entire objective. The technical name here is causal language modeling, and the math that rewards good guesses is called cross-entropy loss. You can think of it like a score that gets lower when the model's probability mass sits on the right answer and higher when it spreads mass on the wrong ones. The intuition here matters more than the exact details. High probability for likely next words, low loss. Low probability, high loss. Over billions of examples, the model internalizes patterns about which words tend to follow, which in which contexts. So at this point, the model has learned a map of language likelihoods, not a database of verified facts. When you think about what's actually happening here, it's remarkable. From pure text exposure, these systems pick up grammar, style, and even some reasoning patterns, without any explicit rules. But there's a catch hidden in the math. Cross-entropy doesn't know truth. It only knows whether the model's guess matches what was observed in the training data. If a wrong fact was common, or the right fact was rare or missing, the probability landscape tilts in the wrong direction. That's the first half of the puzzle. The goal is fluency under the data distribution, not accuracy against reality. Okay, let's hop from training to the moment you type a prompt. The model takes your words, turns them into tokens, and computes a probability distribution over the next token. Then it picks one, either the single most likely token or something from the top of the distribution if you allow sampling, and appends it. Now that becomes part of the context for the next prediction. Every time you see a long paragraph appear, that's what's happening. One token at a time, chained together. Here's the important bit. An early mistake can tilt the context, which shifts the next probabilities, and errors can snowball. Let's pause on decoding strategies for a second, because they shape how errors show up. If you always take the top token, greedy decoding, you get consistent, often boring answers that still reflect training biases. If you sample from the top few tokens, top K, or from the smallest set of tokens whose probabilities add up to a threshold, nucleus sampling, you get variety, but you also open the door to plausible fiction. Fair warning, this is where it gets a bit dense, but stick with me. Sampling is like saying, don't always say the most likely thing, say something that's likely enough. That's great for creativity. It's risky for facts, because the model's notion of likely enough is learned from text, not validated against the world. Quick reset, training optimizes for next token probability. Generation chains those probabilities. Decoding choices influence how much the model wanders. Here's a concrete example, because examples make this click. Prompt: who won the 2022 Nobel Prize in Physics? Imagine a model trained mostly on data up to 2020. In its internal probability map, the names Roger Penrose and Reinhard Genzel sit near the top for Nobel Prize in Physics because they appear together often in that context. It looks at the token stream and assigns high logits, raw scores before probabilities, to Roger after 1. After softmax, maybe Roger gets around 0.28 probability, while Alain is down near 0.03. The model takes Roger, then completes with Penrose, and the pattern continues. And Reinhard Genzel. Don't worry if the numbers feel abstract. The key idea is that the right answer has low probability because it was barely present in training, so the model confidently selects the wrong, but well-supported pattern. To put it bluntly, the model didn't ignore the truth. It didn't have a reliable probability signal for it. This is what happens every time you ask a general chat model about a breaking news event past its training cutoff. It will weave together high-likelihood patterns from history and style, and if you don't constrain it with updated information, it will sound right while being wrong. If you're a product manager trying to spec an AI feature, this explains why a chat with our knowledge-based tool might spout confident nonsense unless you ground it in your actual documents. The generation engine isn't faulty, it's ungrounded. Here's the part that still amazes me. With no direct access to the web or a database at generation time, these systems can synthesize coherent multi-paragraph answers, code snippets, and translations purely from statistical patterns. That's a testament to the transformer architecture and the scale of training. But coherence is not correctness. Those are different levers. So why the confidence? Why do the words sound so sure? Because style is part of the pattern. If the training data includes a lot of authoritative writing, papers, docs, confident forum posts, the model learns that authoritative tone often follows certain structures. It mirrors that tone, even when the content isn't grounded. To keep us oriented, tone comes from patterns in style. Content comes from patterns in text. Neither guarantees a hook into reality. This connects directly to how you use tools like ChatGPT, Gemini, or Copilot at work. When they summarize a report, draft an email, or explain a concept, they're leaning on probability. If the task requires facts tied to a source, like compliance notes or medical guidelines, you need another component in the loop. Enter retrieval-augmented generation, or RAG. That's a fancy way of saying, before the model answers, fetch relevant documents and feed them in as context. The model then shapes its probabilities around that grounded text. Here's how I like to think about it. The model brings language skill, retrieval brings reality. Put them together, and you get answers that are both fluent and anchored. So far, so good. We've established that hallucinations aren't random. They're a natural consequence of optimizing for next token probability without a truth check. Let's talk about when hallucinations get worse. Vague prompts invite extrapolation. Tell me about Paris. Leans heavily on common associations with Paris, France. Ask about Paris, Texas, and you'll get something different. The more precise you are, the tighter the probability landscape. Long outputs also raise the risk. Autoregression compounds small errors across many tokens. One wrong name can force a whole paragraph into the wrong lane. Short, structured responses, lists with constraints, quotes with citations, create checks along the way. If you're keeping score, we're now at the point where vague or long prompts raise risk, and constraints reduce it. In production systems, this is where guardrails show up. You'll see templates that ask the model to extract, cite, and quote exact lines. You'll see retrieval tuned to overfetch relevant passages. You'll see post-processing that verifies references before surfacing an answer. I'll be honest, evaluation adds another twist. Many benchmarks and user ratings inadvertently reward confident, complete answers and penalize hedging or, "I'm not sure." If you train a model to please that signal, you nudge it toward confident guessing. The practical upshot: if you care about reliability, design metrics and feedback loops that score "I don't know" appropriately. Give models space to abstain when the probability landscape looks flat. Let's pause there for a second. We've covered training on probability, token-by-token generation, decoding choices, the snowball effect, and how prompts and incentives shape behavior. To ground this in reality, this is what's happening when your IDE's code assistant suggests an API call that looks right but uses a deprecated parameter. It learned the pattern from older code snippets, and unless your context includes the latest SDK docs, probability can outweigh correctness. Back to our PM from earlier. They deployed a chat widget over their policy PDFs. People started reporting confident wrong answers. Once the team added retrieval with chunked documents, demanded that the model quote exact lines, and tuned sampling to be less adventurous, the hallucination rate dropped dramatically. That's a lot of moving parts. Here's the simple version. The model is a probability engine. If you need truth, give it truth to anchor to, limit the room for improvisation, and reward the system for being honest when it's unsure. There are a few common misconceptions worth clearing up. One is that hallucinations mean the AI is broken or unintelligent. In reality, it's working exactly as designed. It's a statistical model of language, not a reasoning oracle. Expecting human-style truth-seeking leads to disappointment. Another is that throwing more data at the model eliminates hallucinations. Scale helps fluency and coverage, but if the objective remains next token prediction, you improve style and breadth more than you guarantee accuracy. Quantity doesn't fix objective mismatch. To put it another way, More words taught it to sound better, not to validate facts. A third misconception is that retrieval solves everything. Retrieval reduces hallucinations by shifting probabilities toward relevant evidence, but the model can still ignore or misinterpret what you feed it, especially if the prompt buries the context or the retrieved text conflicts with learned patterns. If you're feeling a little skeptical, that's healthy. The gap between sounding right and being right is the whole story here. What this means in practice is straightforward. Ask for citations when facts matter. Ask the model to both answer and show the lines or URLs it used. You'll quickly see when it's guessing. Use specific constrained prompts, names, dates, locations, and the exact format you want. List 3 facts about Paris, Texas with sources is far safer than a wide-open, "Tell me about Paris." Combine the model with retrieval or fine-tuning for your domain. Feed it your manuals, policies, or intranet pages at answer time. If you run a help desk bot, make sure it pulls the latest KB articles into the context window before generating. Calibrate decoding. Lower temperature and narrower sampling for fact-heavy tasks. Allow more diversity for brainstorming or creative drafting. You're trading variety for reliability, and evaluate with incentives that reflect your goals. If you're scoring a model, give positive credit for correct answers, neutral for unsure, and negative for confident wrong answers. That changes how the system learns to balance confidence and caution. Before we go further, let's anchor one more mental model. The model doesn't know the world. It knows what words often follow other words in the kinds of texts it has seen. When you change the input, by being specific, by adding sources, by adjusting decoding, you change the probability field it walks through. To put it simply, shape the field, shape the answer. You've probably seen this without realizing it, when a search engine shows an AI-generated summary with citations underneath. That's essentially retrieval-augmented generation, with post-processing to highlight the evidence. It's not perfect, but it's a deliberate attempt to bridge probability and truth. Here's a short checklist that I find useful. If the task is fact-heavy, ground first. Retrieval, citations, quotes. If it's open-ended, give constraints, word limits, formats, and scope. If quality matters, tune decoding toward determinism and test with withheld examples, and always include a way to gracefully abstain. Hold on to this idea. Hallucinations are not bugs to be swatted one by one. They are a property of the objective function. Let's wrap the mechanisms with one last scenario because repetition from a different angle helps. Imagine an internal sales assistant. A rep asks, "What discount did we offer Acme last quarter?" The model, ungrounded, generates a likely-sounding answer based on common phrasing in past deals. Sounds professional, feels right, might be wrong. Add retrieval over CRM records and insist the answer must quote the line from the contract. Suddenly, the same probability engine is fenced in by real data. So at this point, we've got the mental model pinned down, probability versus truth, and the tools to tilt probability toward reality. And here's the third thing that still amazes me. The engineering community built layers around these models, retrievers, rankers, verifiers, calibrators, to compensate for a core objective that was never about truth in the first place. It's a clever system of systems response to a deep constraint. A quick note on failure modes before we close. Bias in training data amplifies common errors. If a misconception is popular, the model will reflect it with high confidence. Conflicting sources can confuse attention. Extremely recent facts beyond the training cutoff are simply out of distribution, and long conversational sessions can drift as the context window cycles older tokens out. That's the first half of mitigation. Know where it breaks, so you can design around it. The second half is operational. In production systems, you'll often see monitoring for hallucination-prone prompts, fallback flows that switch to retrieval-only answers, and human-in-the-loop review for high-stakes responses. The AI isn't flying solo. It's part of a larger process with checks and pressures. Just to ground this one last time, this is what happens when you open Microsoft Copilot in a spreadsheet and ask it to explain a trend. Without pointing it to the exact range and definitions, it will lean on patterns from generic business language. Specify the cells and time window, and the probability field tightens around truth. If you remember nothing else, remember this. Large language models are expert next word guessers. They are not built-in fact checkers. When they hallucinate, they're doing their job as defined by their loss function, not failing to be human. One last micro recap. Training sets probability. Decoding expresses it, prompts and retrieval shape it, and evaluation incentives nudge tone and caution. The real-world implication is liberating. You don't have to treat hallucinations as mysterious. You can engineer them down. Be specific. Ground with retrieval. Calibrate decoding. Reward honesty. And measure what you actually care about. If this helped clarify how AI hallucinations work, a like and subscribe helps us make more of these.